Two scientists from the University of Queensland presented a mathematical model suggesting that time travel could be achieved without encountering any paradoxes. Germain Tobar and Dr. Fabio Costa developed this model by combining closed timelike curves, as predicted by Einstein's general theory of relativity, with classical physical dynamics. However, as with any theory, this model cannot be accepted as correct without experimental validation. Hence, it's fair to say the scientist's claim is quite bold. What makes this model particularly intriguing is its fundamental difference from other time travel theories. It doesn't involve any quantum equations. From this perspective, the model becomes both unique and relatively easy to understand. Furthermore, it doesn't introduce new theories. Everything is explained using existing classical physics. This is a remarkable development for science fiction enthusiasts and time travel enthusiasts alike. Einstein's theory of general relativity predicts the existence of time loops, where events can occur both in the past and the future. This theoretical insight fundamentally changed our understanding of physical dynamics. Tobar describes a theory unifying general relativity and classical dynamics as the holy grail of physics. But a critical question arises: is time travel really possible without paradoxes? According to Tobar, nature itself seems inclined toward this possibility. The paper suggests that events in time loops would somehow align into a consistent order. This means that even if someone tried to change an event in the past, the system would self-correct, neutralizing the change. This concept of self-correction is key to avoiding paradoxes and lightly touches on simulation theory. To understand the model, let's consider a scenario using the COVID-19 pandemic. Imagine a time traveler goes back to prevent patient 0 from being infected. At first glance, this intervention might seem to prevent the pandemic. However, if the pandemic is averted, the time traveler would lose their motivation to go back in time. This creates the classic grandfather paradox. Tobar and Costa's model argues that such paradoxes are impossible. If patient 0 is saved, the system would find another way for the pandemic to begin. Perhaps the virus infects another individual, or the time traveler's intervention itself triggers the pandemic. In this way, the causal chain remains intact, ensuring the pandemic's occurrence. This concept, which nods to the idea of time police, is explained by the scientists using concepts of information and thermodynamic entropy. Both information entropy and thermodynamic entropy deal with the transition from order to disorder. According to the model, events on a macro scale remain unchanged because micro-scale events are rearranged to preserve consistency. The system balances every local intervention with a counter effect to maintain global coherence. At time t before time travel occurs, the system's entropy level is balanced at point. Traveling to the past decreases thermodynamic entropy, pulling the system to point level of minus level x. However, during time travel, information entropy increases, adding x units of order to the system. This process restores the system's total entropy to level of. This explanation shows how both thermodynamic and information entropy create a balancing mechanism, ensuring the overall consistency of the system. Thermodynamic entropy's decrease makes backward time travel possible, while the increase in information entropy ensures the process proceeds orderly and paradox-free. In essence, time travel can occur without disrupting the universe's entropic balance. For instance, even if you try to prevent a pandemic, the system adjusts by decreasing information entropy, ensuring the pandemic still happens. Every intervention by a time traveler is rearranged by the system to maintain overall consistency. Mathematically, this means the impact of any event on the entire system is neutralized. According to this approach, a past event's non-occurrence is physically impossible, and a time traveler must relinquish their free will in the past. The model is undoubtedly theoretically fascinating, but also open to significant criticism. The paper relies entirely on a mathematical framework and offers no experimental evidence for the existence of closed timelike curves. This raises questions about the model's applicability to the physical universe. Additionally, testing entropic balance experimentally appears implausible. which is arguably the model's weakest point. The paper suggests that actions taken in the past are rendered ineffective, which severely limits the concept of free will. If nothing in the past can truly be changed, then what's the point of time travel? From this perspective, making massive machines for time travel seems far less practical than simply watching old movies. The model is grounded in classical physics laws and doesn't account for the probabilistic nature of quantum mechanics. This could lead to conflicts with phenomena like quantum entanglement. Tobar and Costa's model offers a bold mathematical framework that could make paradox-free time travel possible. The idea of events rearranging themselves and the reduction of information entropy make time loops theoretically consistent. However, experimental validation of this model is currently impossible and raises profound philosophical questions about concepts like free will. While the theory is an impressive mental exercise, its practicality seems far removed from reality. Let's not forget that 100 years ago, people believed riding in vehicles at speeds over 30 km/h would cause the heart to stop. Perhaps this imaginative paper, inspiring our video, might one day lay the groundwork for future technologies. See you in the next video.